All right. Well, thank you. Thank you. Welcome back, everybody. We are going to be blessed to learn about the formation of land during the creation week. And I haven't heard a talk on this. And this is you're going to be hearing Harold Gilbert. He's got his master's degree in aerospace engineering from Auburn, and he's worked for the Defense Department for over 30 years. And he's been following this hydroplate for, oh boy, 30 years. And he helped Brian Nickel put together helped him understand what the fountains of the Great Deep would do with the atmosphere. So we are incredibly blessed. I don't want to take up any more of your time, but Harold Gilbert, everyone.
Hi, my name's Harold, as Brian said. Thank you, Brian, for the introduction. Um, yeah, like Brian said, I'm going to talk about the potential solution for formation of land created during Creation Week. And I assume everybody can see my slides before I proceed. Is that true?
Yes, yes, I see him.
Okay, good. All right. All right, so my presentation actually has two different parts. First, I'm going to kind of review a natural process. I'm an engineer by nature. My wife thinks that anyway. So I like to think things through. And so one of the things I want to talk to you about is sort of like a natural process for creating land. So I want to start with the initial condition that God creates the hydroplate that, and then to talk about what is that primary unbalanced force that drives the motion of the crust. And basically it results in dry land is biased around the equator. Now, when I say that I'm talking about between plus or minus 30 degrees latitude. So that's obviously within the tropic and subtropic region. So once I establish that, then I'm going to talk about the evidence for dry land. The benefits of the dry land being in that particular region. All right, so let's get started. Okay, so of course, God creates the world, the earth, and it looks like He created an earth that is a water world, right? It is basically water that surrounds the earth. That is, of course, in verse 2 of Genesis 1. And we can see that from a lot of the different things that mentioned in that particular verse, right? That the earth was formless, that the Holy Spirit hovers over the waters, that sort of thing. And it gives us an idea that the earth is a water world. Now, on day 2, God creates the crust in the water, right? That's the hydroplate. So that's kind of where I start. I start with this condition. First, there's two things I want to talk to you about. First, though, is there. Notice that there's a natural time delay between when God creates the hydroplate here, the rakia, the expanse between the waters, and when land is created on day 3. So that natural time delay sort of indicates to me that there is a natural process going on, right? I mean, God could have easily just made the crust and the land all in one day, just 1 second, really. So it seems to indicate to me that then there is sort of a natural process. So the second thing I want to point out is that this crust is very unstable, right? It's not in equilibrium. It's very difficult for that plate to actually stay up like that. That water below is actually is not a very structural sounding thing. So the crust is going to collapse in parts and it's going to rise in parts. So the question is, where does it rise and where does it come up? So that's kind of what I'm going to talk about. Now, I think currently what hydroplate theory proposes is that it is a random sort of rising and collapsing of the plate. So I want to talk to you about that. It's actually a natural pattern that it emerges. All right, so God doesn't really tell us in the Bible what the crust of the thickness is, nor how much water is above, nor how much water is below. So we have to assume those. Now, hydroplate theory proposes about 100 kilometers or 60 miles. And so that's kind of where I start. That's kind of an established parameter. Now, the volume of the water, I choose values between 0.7 to 1. Now, I'm not sure exactly what that volume is. I'm just sort of estimating it. It could be less than that. It could be more than that. And then the volume of the water below. Now, I use what's called a water volume ratio, and I use values between 1.7 and 2.3. So just to give you an idea what that means is that if you have values of about 2, that means that there's going to be twice as much water below than there is above. So just to give you an idea what that means. The assumption is that the expanse, the firmament is made of granite. That's, again, part of hydroplate theory. And the next assumption is assumption for me, actually. I assume that the crust is uniform in this sort of initial guess with a constant thickness and density. Now, I go back and change that, but I do this initially just to make it simple on myself. The equations are much easier to solve, and also gives me an idea of kind of establishes what will happen. So anyways, there's no other things that we need to think about. That water is going to be sealed in. It can't escape. That's a very important parameter that must be kept. And that makes a lot of sense because the crust, if you go down about 5 kilometers, it enters into the plastic flow region, which means any cracks that are in there will actually disappear. And so anywhere from 95 down to 100 kilometers, it's going to be, all those cracks are going to be filled in. So it's going to make a sealed granite so that water can't escape. Now, the volume of the water below is going to be constant during the collapse. Now, initially, when that crust of the water crust actually sits on the water, it's going to change its density. But now, what I'm talking about is during the collapse, that volume actually is going to be constant, and that's from the conservation of water, and also that water is incompressible. So those two things makes the water of the volume below stay constant. Also, the crust will maintain its thickness throughout the collapse, during the collapse as well. So that's sort of a minimum energy requirement, because if you allow that crust, it can actually stretch or it can actually compress as well. So, but a minimum energy requirement says that therefore it stays the same. There's no compression or or stretching. So what is the unbalanced force? So there's a thing called the lithostatic pressure, which is basically the pressure from the weight of the crust that sits on the water. Now, that depends on the crust thickness, depends on the crust density, and also depends on the local gravity. Now, I assumed that the crust thickness and density are constant. Therefore, the only thing that's going to vary is that gravity. So I ignore the hydrostatic pressure and also the atmospheric pressure because they're really small as compared to the lithostatic pressure. Now, you know that the gravity actually varies over the surface of the Earth. That's based off this WGS 84 standard. And it says that gravity is actually 0.7% higher at the poles than it is at the equator. So if you go on vacation, you need to go to the equator because you have less weight there. So, but anyways, and there's two reasons for that. The poles actually is closer to the center of the Earth than the equator. The equator, the Earth actually has a little bulge to it. So that is one thing that affects the gravity. The other thing is the Earth rotates. So that actually offsets the gravity as well. So if you were to plot the lithostatic pressure versus the latitude, you'll get this plot. So at the poles, this is the South Pole, 90 degrees latitude, it has this little dip to it. And at the equator is less pressure. And at the North Pole, it's got greater pressure. So this sort of indicates then that there's going to be a bias, of course, towards the equator. Now, the gravity is not that much. It's only about 0.7%. And if you were to start thinking about putting tolerances in there, that's going to be greater than the gravity. And so my analysis later on, I'll show you what happens there. Okay, so there should be a series of events that goes on, right? So the plate starts to collapse towards the center of the earth at the poles. And then, of course, the water underneath it's got to go somewhere, right? So I propose that it migrates towards the equator. And of course, it pushes up on the plates and pushes it out of sea level if you have enough water underneath. And that is one of the criteria. So once that plate pushes it up, the water above will go to the North Pole and of course, to the South Pole. And that it's just a runaway process, and it won't stop until the crust actually reaches the mantle. So, and the big question though is that if there's enough water, then land will emerge out of that water. All right, so this is gives you a better idea what it looks like. These are drawn to scale. That x-axis is drawn to scale, and I'm sorry, the y-axis, and then the x-axis. Now, it doesn't have the right aspect ratio, nor, it's going to be, in reality, it's going to be curved, and this one's straight. But it's just an idea, it gives you an idea of what it looks like. This is the water above and the pre-collapse configuration. Now, this one I used 0.7 ocean volumes above. That's, 0.7 times the current ocean volumes right now. And I used the ratio of 2.15. So in order to determine the water below, you multiply 2.15 times 0.7, and you get the volume of the water below. All right, so this is a pre-collapse. The post-collapse, it looks like this. The water congregates at the South Pole and at the North Pole, and you have the water underneath at the equator. Now, in this particular case, it creates an equatorial supercontinent. Now, I'm not proposing an equatorial supercontinent, but this gives you an idea that there is this bias towards the equator. So I went back and through it, and I actually incorporated a crust tolerance. So the idea of the crust tolerance is, anywhere from 0.1% all the way up to 0.5%. So 0.1% crust would be anywhere from 99 to 101. So that 1% is 1% of the 100 kilometers. Of course, 5% would be anywhere between 95 and 105. And of course, I did like a random distribution throughout the whole crust. And you can see this is the plot of it. The black line is that basic, simple assumption. And this is where you put in the pressure with the 1% tolerance level. Now, what's interesting is you'll see that the actual data, actual pressure still follows a curve, still follows that gravity curve. So it's not biased along a straight line; it's biased to a curve, which is kind of interesting. All right, so if you look at the table over here, I put what the minimum pressure is, where that crust, the peak should come out of the water into these buckets, plus or minus 5 degrees latitude, and all the way up to plus or minus 30 degrees latitude. So at plus or minus 1% tolerance, I get 100% of them. The peak will actually come out of the water 100% of the time between this plus or minus 30 degrees. And if it go down to plus or minus 4%, it's still 88%. So that's still a very likely chance that the crust or that peak will come out somewhere in the latitudes, in that plus or minus 30 degrees latitude. Now, once you get to plus or minus 5%, you can see that this goes down pretty low. Now, this is I did all this in Excel. I used a random distribution function in there. And for this one, I did 120 cases for all of them, which I was hoping that would be the statistically equivalent or significant. Sorry. So my bottom line then is even tolerances up to plus or minus 4%, I still can get that peak to come out of the out of the water in the tropic and subtropic regions. All right, so just to give you an idea of how I did my analysis, so one of the equations that were pretty important is that volume, constant volume. And so this is the constant volume below in the pre-collapse is equal to the volume below in the post-collapse. So that will actually help me to determine what this height is above the height of that water. And from there, I can then establish, okay, add how much of the crust thickness that there is. And then I would have to reorganize the water above. That sea level will actually change. And this probably is probably the most difficult part here, and the one that was most difficult to determine. I had to use the goal-seek function in Excel, which is based off a Newton-Raphson method. And so you put in you guess, and it will actually go through and determine what the right answer is, usually, but not always. Okay, just to give you some idea of the plots, again, I use 0.7 to 1 ocean volume above. And if you go down and look, and this is, this is the height from sea level versus that water volume ratio. So if you go down here, like at 1.7, the actual volume doesn't go above the actual crust. The peak doesn't go above the height above the sea level. So it's still all underwater. Then as you continue to increase that water volume below, it actually will start coming out of the sea level and start, coming out of the sea at about 1.93. So that 1.93 is very important, and I was surprised that they all came out at that same ratio. So no matter what volume you use above, I think you're going to have to use 1.93 if you want. That's where you have to at least start to get that water to come get that crust to come out of the water. Now, if you go up to the 2.3, you can see how much of the sea level, how much it rises out of the sea. And somebody's asking if how much how high the mountains were. According to my model, they were fairly low. So this is a plot of the land area and percentage of the total Earth surface. And you can see that all the data falls on this same line, which really surprised me. And as a matter of fact, I thought there was a mistake in my process, but anyways, it didn't appear to be. So today there's land surface is about 30% of Earth's surface, right? So if you were to have that same sort of mind that, okay, in the pre-flood world, 30% of the land comes out, then you would have to use a value of about 2.3 in order to have established 30%. Now, I actually believe the pre-flood land was only about 15%, and I'll discuss that a little bit later on. But you can see that then I would use a value of about 2.04 for my particular analysis. So I was surprised. Now I tried to vary the thicknesses of the lines here to kind of show you, but I doubt you can see that. And I also had a problem down here below to calculate it, because that Newton-Raphson method, it has problems when you have slopes of infinity or slopes of zero as well. So anyways, I had problems merging, but I know in the previous chart that number is about 1.93. All right, so I having an engineering mind, I thought, okay, what happens when you change the crust thickness? And so the black line is that 100-kilometer crust is what currently hydroplate theory proposes. Then I changed it to about 30-kilometer crust, and I don't know why I changed it to that. I was thinking for some reason that was kind of like the average crust thickness today. But anyways, you can see they don't vary that much. So as a matter of fact, they're parallel lines. So if you have 30% and you want different values, you want to know what that water volume ratio has to be. It has to be within this 2.3 to 2.34 or whatever that is, 2.36. So it doesn't vary that much. So that water volume ratio then is pretty important. It is a pretty important parameter to know. So if you can define how much water you want above, it defines how much water you have to have below in order to create land. All right, so kind of switching gears, I'm going to talk about sort of the benefits of having land in the tropics and subtropic regions. Of course, everybody knows that being at the equator has a lot of advantages, right? You can support larger animals. All the elephants, giraffes live at or near the equator. You have a higher biodiverse ecosystems. Of course, temperatures are constant year round. You have higher volume of rainfall, higher density of biomass. So there's a huge amount of advantages, and you could probably think of more. I just sort of threw down some ideas. Now there actually is a disadvantage. So if you were to put all 30% of the total Earth surface area at the equator, then that would pretty much engulf about half the tropic and subtropic regions. Of course, now that is a lot. So it would probably create deserts in the interior and all that kind of stuff. Now, obviously, I don't have a climate model of that, so I'm not sure if that's true, but I think that would be true. So that's why I propose that we choose the original continents to be about 10 to 15% of Earth's crust, our surface. Sorry. Okay, so one thing that's important to me is matching the biblical account. Now, this is what God said. God said, "Let the waters under the heavens be gathered in one place, and let dry land appear." Now, of course, God said, "Call the expanse heaven appear." So let the water under the expanse be gathered into one place, and let dry land appear. This is a cause to effect sentence. Of course, the cause event is the water that gathers into one place, and the outcome is, of course, dry land emerges. So again, this kind of matches my model. The water gathers together into one place, and of course, dry land appears. Now, dry land is actually driven out of the water above. So that appears to actually fit the biblical narrative than the traditional view, right? The traditional view believes that the waters under the heavens, which will be kind of our ocean waters today, was all covered the earth. And of course, God collected all that water together and made dry land. Now, what happens though if you were to let go of that water? I mean, it's not a very stable situation, right? The water would just go back to where it was. So that land has to be driven out of the water below, out of the water above. So that is a very important point. And also the secular models have problems creating land, which is very fascinating to me. It's just difficult to get land to come out of the water. All right. There's also evidence of a major uplift. This is some data that's in the secular articles. They talk about what they call sheet erosion. That there's zircons that were existing and they were together, and then some water event happened that separated the zircons, and they were separated evidently by water. And these things cover like huge areas. I was surprised by how much they actually cover. Say 20. That's a long ways. Of course, these sediments here do not have fossils in them, so there's no plant. So this is, of course, before when plants were existing. Of course, that to me is day 3, or the beginning of day 3, I should say. Now, the secular interpret this as having these huge mountains occurring, right? Coming out. These mountains were big as the Himalayas, and that they have that water that runs off. But of course, if they're creating mountains over millions of years, then that's actually not going to happen, because that the mountain's going to take, years, millions of years to actually get up to that height. And you're going to start having rivers and things like that. So you wouldn't have a straight sheet erosion as you see it, the evidence is. And of course, my interpretation then is that this is actually goes to the original continents that were created during creation week. Of course, there's that crust that came out of the water, creating the erosion. Of course, the fossil record also points to there being that they lived and died, that the animals, the plants lived and died in warm climate. They have very little temperature changes throughout most of the geologic column. So now that's a problem for the current paradigm, because this is actually, I should say, this is the a map from the Paleobiology Navigator, and you can go and see where the fossils are buried in our current map of the world, of the Earth. And also then you can go and say, okay, where did they died when they were alive? And of course, this is where dinosaurs died, and this is where their fossils were located. Of course, they think that Pangea existed, and they actually can plot this where they lived. But now you can see that there's a lot of them that died in the North Pole, and there's a few of them that actually died in the South Pole. Now that's a problem, because in the paleoclimate models, they try to go back and try to make the whole Earth warm, right? And of course they failed miserably, because it's very difficult to do that. And one of the primary drivers of weather, obviously, is the sun. And so you have very shallow angles of the sun rays hitting the North and South Pole. So the Earth is not going to be heated evenly. And trying to compensate for that is very difficult to do. So they even tried some unrealistic mechanisms to do that. So now they're sort of stuck with the polar dinosaur idea. So that's what they're advocating, and you can actually see YouTube videos of that. And they're also incorporating that into current movies and things like that. My model also sort of predicts that there would be these extensive shallow coastlines. And you can see kind of the slope of the coast. The lines are from 2.3 kilometers. You can walk horizontally. You only drop about 1 meter in altitude. So that is a very shallow coastline. Now, why is that important? Because the pre-flood world had a lot of marine animals, marine life. So just take, for example, the coral reefs. Today, coral reefs only cover about 284,000 square kilometers, which is about 0.08% of ocean volume. And in my model, it'll be more like 9 million square kilometers. And of course, coral reefs only exist in waters less than 50 meters. So that would be about 2.5. That's 31 times what we see today. So you can see how much marine life there would be. If you go to Wikipedia, that talks about the coral reefs supporting like 25% of the marine life in the oceans, and so that's a huge amount. And you can imagine if you multiply that by 31 times, you'll just have a humongous amount of marine life. Of course, also God talks about in Genesis 1:22 that he tells the fish, be fruitful, multiply, and fill the waters of the sea. And of course, you can imagine if they fill the waters of the sea, then they can really fill a lot of their pre-flood world oceans. Now, interesting, of course, he doesn't tell that to the birds nor to the land animals, but he does tell that to the mankind to fill the earth. Now, after the flood, he tells the birds and land animals to fill the earth, and he also tells that to mankind again. But of course, mankind is prone to not do what God wants. Okay, so evidence for the shallow seas. there's marine life sediments that make up about 75% of the geologic column. I mean, and marine life is found all the way through the geologic column, not just in the bottom part, but all the way through. There's also these what's called these subcambrian peneplains, and I have a picture of it. They're found in Norway, Sweden, things like that, and they're just flat as pancakes. They have relief less than 20 meters, which means the depth only goes down about 20 meters as far as the eye can see, which is about 10 kilometers. So this, of course, goes underneath the geologic column. So this existed prior to the Cambrian explosion. All right, so also this belt supergroup, they talk about these shallow seas that cover just huge areas. And they actually have names for these, these seas, and they're all over the earth, right? They're in Europe and Middle East and things like that. So this is, of course, is where the geologic column is. And of course, they have to have those shallow seas in order to get all that marine life. All right, so that's basically the conclusions. And so basically, I reviewed natural explanation for the configuration of land during the pre-flood era. I said that this will be biased around the equator to have a crust thickness, even if you have crust thicknesses of about plus or minus 4%. And of course, that most important variable is the water volume ratio. Of course, I've provided historical and observational evidence. And okay, so in my mind here, young Earth models, obviously, we know the truth that the Earth is only 6,000 or 7,000 years old. So we really have to be very efficient and optimize our land, especially in the pre-flood world, in order to match all the data that's available and match all that geologic column, things like that. So I think it's very, very good if we could think of having land that's created around the equator. All right, I think that is end of my presentation, and I'll start looking at questions.
All right. Well, thank you so much for that, Harold. Man, there was a lot of stuff I didn't know there too. Thank you. That was wonderful. Let's see. That was interesting about how it would spin like that. Let's see. The question from John is: could the water being gathered into one place and being called seas be synonymous with the pillar formation in the Great Deep? Is what John asks.
Okay. Okay. Yes, the water is called seas. Now, the idea of seas, I guess, is to gather the gathering of waters. That is actually one of the definitions of seas. So it'd be synonymous with the pillar formation in the Great Deep. Yeah. Now, so that crust thickness variation. Now, I just showed you kind of the simple idea. Of course, that was just easy to determine the math, but if you have thicknesses, you can then have variations, and some of those plates can hit the mantle as well. So, and that would be sort of a random thing, and I'm not sure exactly where or anything where that would occur.
Okay.
So what is the relationship between the water under the granite versus the water that flowed out of the garden? So one of the things, if you notice that the garden, it has the water flowing in all directions, right? North, south, east, and west. And of course, the idea here is if you have this sort of the continents gathering near the equator, it's very easy to see that north and south, right? Because the mountains will come up, peak up there, and then you can have variations, obviously, in the longitude directions as well. And so that would indicate that you can have a place where it flows in all directions.
Okay. And how do you see tidal pumping affecting your presentation?
Okay, so of course this is sort of the initial land configuration. Um, and again, some of those pillars may actually touch the mantle as well. So as this progresses throughout the pre-flood time, then yeah, I can see that the moon will have effect on the water below. So that's, of course, that's over time. This is sort of a short snapshot of right, on day 3. So
Good. Was the water above fresh water?
I don't know. I don't know the answer to that.
Interesting
Yeah.
question.
Yeah.
Yeah, very interesting. All right.
There's another one here. There between the northern Germany, Denmark, southern Sweden. It's called the Belt. Is this the Precambrian shallow sea fossils remnant? I think so. I think so. Yes. I don't. I'll have to get more information on that, but I think that is.
Oh, and also, if everything was very good, people could drown in the seas. Any thoughts on that?
I'm sorry. What?
If if God said everything was very good, but people could drown in the seas, would that be a danger? Could there, versus,
Well, of
any
course, the
thoughts on that?
garden. God set the garden up, right? Of course, He probably set that up on high, the peak of the uh, where the land comes up. So that's going to be a little bit ways from the water. Of
Oh,
course, that's all shallow water too. I mean, you'd have to walk 2.5 kilometers out just to get it to go above, your
okay.
body, I guess. So it'd be very difficult to drown in that sort of thing.
Yeah, I skimmed that question. You said, could it have water been more buoyant back then? The result
Uh,
in floating kind of like the Dead Sea, where you can,
so to be more buoyant, you have to be a little bit more dense. Um,
right, right,
so I don't know if there's any evidence for that. And of
right.
course, the fish have to live in that water, so
That's true.
I I don't know if that would be the case. No.
Okay. Interesting questions. Would it be possible for the Earth's bulges, which the moon changes every day, to process through different latitudes so that no place on Earth stayed in the tropics or at the pole regions all the time, similar to the bowling ball illustration?
I have not
Interesting.
thought of that. So that's a good question. I
Hmm.
think that weight of that plate would probably be very difficult, but it is sitting on water. So, um, hmm.
Interesting. Very, very, very interesting. Yeah, I never really thought about what it would be like before the flood and how it all get put together.
Okay, you said water is incompressible. Yeah, any liquid actually is incompressible. That's kind of one of the things unique about liquids. Of course, that's how you get hydraulics as well, is because the incompressible part. Now, when I say incompressible, it's obviously if you have huge changes in pressure, it will change that pressure. As a matter of fact, when that initial plate was put on the water, it probably lost about 10-11% of its volume. So the density went up. But I'm talking about kind of over smaller volumes or smaller pressure ranges. It can be considered incompressible.
Hmm. Interesting. Yeah, incompressible. I think I remember Walt Brown, or I think it was Bob Enyart talking to Brian Nickel about that, the incompressibility, because they don't use water in the hydraulics. But he says either term is entirely appropriate, just directing all to the term they like to find in the tables. Okay.
A couple of other thoughts that I have too is, you know, if all the continents were kind of around the equator, then there still could be ice and stuff at the poles, right? You could still have, you know, so I mean, because nobody lived close to them, and because all the land animals and stuff doesn't mean there wasn't, polar caps at the poles. So that's still possible, and of course that's kind of what it is today. So it makes sense that there would be. Um, so the tidal effects will still have tidal effects, right? And that will move the water up and down quite a significant ways. There won't be any waves. Be very calm water around these continents because the waves will break, very far away, 2 or 3 miles before they get to there. So the waves would be pretty calm. Now I'm not sure about one thing I was thinking about too is the weather pattern exactly. I'm not sure how that would work. I'm not an expert in that. So if anybody has any thought about exactly what happens if you put most of the continents at the equator, what would that do to the weather patterns? I'm not
Hmm.
sure. Of course, the marine life that's right there in the shallow waters. Of course, marine life is at the bottom of the food chain, so that will help support all the large animals, things like that. Um, I mean, nearly everything eats fish, I think, right? Especially like birds and land animals, things like that. Of course, there's talk about having the dinosaurs, live in these sort of a marine environment type thing. There was a push at one time. I don't know how far it got, but you can see that they probably live close to that water to get enough to eat.
It was fascinating how a lot of those graphs they went to the same point, and then that one that went to the same line. I'm not sure that I don't know. Would you be able to show us that one again? I want to make sure I got that information accurate. What they
Which
were
one?
looking at
I'm
when
sorry, say that.
there was like four lines that they all intersected at the same point. It was at I think was it something point three? Yeah, that one.
Yes.
Yeah.
Okay, so this is the height from sea level in
Yep.
meters, right? So anything above zero will be underwater. So
Yep.
once the plate collapses and everything forms, that peak is still not quite out of the water. So then they all kind of emerge right here at that 1.93, which is exactly at where exactly where the plates start to emerge
Wow.
out of the water. So again, I thought, gosh, that's weird, that's strange that it
Yeah.
happens all right there. So
Yeah.
I started investigating, and I couldn't find. Well, actually, I did find some mistakes, but then I corrected them, and I still had this here. So, um, yeah.
So that's the ratio of the water under the earth to the ratio of the water above the earth.
Oh,
Is
yeah.
that
Sorry, the water volume ratio is yes. The water volume below the earth and the water over the water volume above. So
okay?
So it's
Okay.
just a multiplier. That's basically what it is. So if you determine it's like zero point 0.7 ocean volumes,
Yep.
and then you come down here and use two, that's two times the ocean volumes. So
Yep.
two times the ocean volume would be below.
Right.
And I was amazed that it was in this particular range as well. I mean, I wasn't sure exactly what I'd get,
Right.
but I quickly figured out that this is the range you need to be.
Wow. Interesting. Very interesting. Fascinating. And then you had that one slide where they all came down on the same line, which
Yes.
was very unusual, I thought.
Yeah, this is land area and percentage of total Earth surface. So if you want it today, it's currently 30%. So if that's what you want to use, then you just go over here and now it's about what 2.3 or so. And yeah, all these fall on the same line, which kind of threw me off.
Yeah. 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 That's quite the coincidence. Wow. Fascinating. Okay. Let's see. We got some more questions here. Let's see where we at. In your theory of land formation, would there be inland seas or just seas at the edge of the continent? If I,
There would be inland. Okay, so that crust thickness, if you vary that, yes, you could have little islands. And in fact, that's kind of what I'm thinking is as it goes down, of course, the crust thickness varies. And so you can have little islands as it goes out. Yeah, that's entirely possible. You can have inlets, outlets. You can have that crust, the peak, vary over the different latitudes, things like that. So,
then it goes
yeah,
on to say, how would the inland seas not be dead quickly?
not be dead.
Yeah, not kind of sure how that would be. I would think it would be just like a big lake, I would think.
Well, you still have, you still have the tidal effect. You still have
Right.
water coming
Right.
in,
Oh, that's true.
and you have water coming out. So if he's talking about dead in the sense that it's stagnant
Mm.
water, but and also evaporation and rain. So I don't get the idea of being
Okay.
dead.
And then pre-flood atmospheric composition might have been different from today, levels of water vapor. Any guesses? Yeah, I know there was more oxygen before the flood. They have evidence of that. Do you have any idea about as far any other part of the atmosphere?
No,
Okay.
no.
Somebody asked about the shallow seas allowing the fish to walk out of the ocean. The joke.
Well, there you go. I didn't think about that.
It always makes me think of when the whales beach on they beach and everybody's trying to push them back in. It's like, well, you're stopping it from evolving. Let
Yeah.
it go.
Now
Uh,
the shallow seas idea is obviously a part of the evolution mindset, right? They have to.
oh yeah.
I mean, the bottom of the Cambrian explosion, it was all kind of marine life, so they have to have those shallow seas as well.
Ooh.
So it is definitely matches that sort of paradigm.
Another one. How did the sea Antarctica fitting into the ring of continental granite around to the equator? How do you see the Arctic fitting into, where did it go? The ring of continental granite around the equator.
Yeah.
So that would be the plates. Let's see. Not quite sure. It's from Ellen's old computer. Maybe she can clarify that a little bit.
Yeah, I just wondered how, if there's any ideas about how Antarctica, what place it would have in the ring of land. Like it's weird that it's at the bottom there. Shouldn't did it slide? If you have any ideas about that.
Of course, yeah, it happens that um, during the flood, right? Is when that occurs. It all depends on how you break up the plates, right? That's kind of the key thing there, and I think Brian does a good job kind of following um, the baseball scene around. So if you start there and you start dividing the plates up, then there could be a situation where obviously where their Antarctic actually moves down. Um, yeah, it's all about how it cracks up. That's the big thing.
Then the polar caps are fresh water. Does that defend HPT? It's low salt in those polar caps.
Our freshwater does this defend HCP? Seems to indicate low. I'm not sure
Personally,
exactly.
I would think it would. It came down as snow. Any ideas? Or we'll move on
No.
to another one. You talk about rain, but is it before the flood? Do you believe there was rain before the flood?
Rain before the flood.
Yeah.
So when this collapses, one of the things I had thought about is obviously there's going to be a lot of mist in the air, right? I mean, you're having part of it collapse, part of it rise. You have the waters moving. You're going to have quite a bit of mist in the air for probably quite a while. So when it talks about it not raining, I assume that's probably the idea. There's a mist and also the springs.
Sure.
So now I don't know what happens after that. I assume there probably would be rain though happening be after that point. Of course, the idea there is that if they didn't know what rain was, then how did they know to ask? There was no rain. That sort of question. But that was, I think there was rain further on.
Okay. And then was the water below the surface fresh? I think he's talking about the subterranean water chambers would be my guess.
Oh yes, they were. I don't know what the initial conditions were. They could have been, yes.
Well, they could have been, but then I think that supercritical water dissolved a whole bunch
Yes,
of
once they
minerals.
start heating up, you'll get a lot of stuff from the crust, a lot of stuff from the mantle, and they'll start intermixing and just because they're heating up and things like that. So,
okay, yeah, I think we hit a lot of them. Yeah, we hit quite a few of them, and they enjoyed it. That was good. Saw some good compliments there. And this was your very first creation presentation, is that right?
That's it. Yeah.
Wow, you did a great job. Did a
Well,
great
thanks.
job. And you certainly didn't copy anybody. I haven't seen any of this information before. Yeah,
Well, good.
excellent. Excellent. And thank you so much again, Harold. You did a great job.
Well,
Great
thank
job.
you.
Thank you.